Today we're going to try and get to the bottom of the relationship between E cell, Gibbs energy and the thermodynamic equilibrium constant, which is more commonly known as K. But let's start on really familiar ground. We've got the Daniell cell here. So essentially I have got a zinc half cell in contact with a copper half cell. I have a high resistance voltmeter in place and obviously my salt bridge. And this high resistance voltmeter is there to measure E cell, the maximum potential difference between these two half cells. We're measuring it under standard conditions, so that's 100 kilopascals, solutions at 1 mol per decimeter cubed, 298K, and no current is flowing. And when that's the case, E cell should read for this particular cell 1.10 volts. Now, E cell is intimately related to the Gibbs energy. We came across this in the last video. If this is making absolutely no sense to you whatsoever, I really strongly suggest you stop right here and go back and work through the previous video, which essentially explains this relationship in a lot more detail. We derived this equation from first principles. So the change in Gibbs energy is essentially the maximum work that this cell can perform. If I replace my high resistance voltmeter with, say, a motor or a lamp, then this cell will start to perform work. Current will flow from the zinc half cell, the negative half cell, to the copper half cell, and the reactions will actually start to happen. So we are saying that in the zinc half cell, zinc is going to be oxidized to form zinc ions plus electrons, and these are the electrons that are flowing around the wire where they are going to reduce copper ions to copper metal. So redox reaction. This reaction is going to happen until equilibrium is released, and at that point the concentrations are going to stop changing. Concentrations of the ions in the half cells are going to stop changing. If zinc is no longer being oxidized to zinc ions and we haven't got any more electrons flowing around my cells run out of energy. It's essentially gone flat, which means there is going to be no more work done. There will be no more change in Gibbs energy. So at equilibrium, we can definitely say there is no more change in Gibbs energy. That is going to equal 0. Okay, another way of saying it is that the system has reached its minimum Gibbs energy. Its minimum Gibbs energy. The concentration, or if we were dealing with gases, pressure of the reactants and products at equilibrium are related by the equilibrium constant K. We should be familiar with this. So K is equal to the concentration of the products over the concentration of the reactants. So in this case, that would be copper and the zinc ions over the reactants, zinc and the copper ions, although of course the concentration of solids is unchanging, it's constant, so we can remove that from the equation. When I put in actual numbers for this, the concentrations of zinc ions and copper ions at equilibrium, then our value of K tells us an awful lot about this reaction. If K is greater than 1, then we know we have a much higher concentration of products at equilibrium than reactants. And the bigger that value, the closer to completion this reaction has gone. So position of equilibrium lies very strongly to the right is another way of looking at it. So we can describe the equilibrium position of a reaction in terms of the equilibrium constant, K, in terms of it being at the point where we have no more change in Gibbs energy, so delta G equals 0, which means that delta G and K must be related. Hey presto, they are. So delta G is equal to minus RT ln K, where the temperature is in Kelvin and R is the gas constant, which is 8.314 joules per Kelvin per mole. Deriving this equation is beyond the scope of A level, but there are plenty of people out there that are doing it very well if you want to know where that equation comes from. But if you're happy just to accept that that is the relationship, we can move on, because we know that delta G is equal to minus ZF E cell, where Z was the number of moles of electrons being transferred, i.e. the current that's moving around our circuit. F was Faraday's constant, so that is the essentially the charge of 1 mole of electrons, and that comes to 96500 coulombs per mole. Okay, so let's put those two equations together. We can then say that minus ZF E cell, so essentially that is my expression for changing Gibbs energy, is equal to minus RT ln K. And I can rearrange that. This is where it actually becomes useful. Ln K is equal to ZF over RT times E cell. So if I know E cell, then I can actually calculate a value for the equilibrium constant, which will tell me where the position of equilibrium lies in this particular reaction. How clever is that? So let's move on and have a look at a sample calculation. Calculate the thermodynamic equilibrium constant, that's K, for the Daniell cell at 298 K under standard conditions, given that E cell is plus 1.10 volts. Remember, if they don't give you a value for E cell, then you can work it out using standard electrode potential data. So, very straightforward. We can jump straight to using our equation. Then K is equal to ZF over RT E cell. So number of moles of electrons being transferred is 2. If you go back to the half equations, so 2 times Faraday's constant, 96500, that would be given to you in the exam, multiplied by the gas constant, also that would be given to you, and the temperature, which is already in Kelvin, 298, times 1.10 volts. And when you plug that into your calculator, we find that ln K is equal to 85.7. So K is equal e to the power of 85.7. So if you're not familiar with this, practice putting it into your calculator. And that comes out to be 1.66 times 10 to the 37. This is a huge number. So very much definitely bigger than 1. So that tells me that this particular reaction between zinc and copper ions, to all intents and purposes, goes to completion. You also note there are no units for K, so don't worry about those. So I hope this has been helpful. If you would like this in the form of a worksheet or some practice questions, then you need to head over to crunchchemistry.co.uk. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.